In this video, let us do a quick problem on viscosity. The problem is not exactly very easy. Motion of fluid between two cylinders, two coaxial cylinders. That is what I have given name to this problem. These are two coaxial cylinders. Cylinders are like this. Let me take help of this prop. Yes, cylinders are like this. There is another cylinder over here, and in between the two cylinders there is a liquid. Liquid has coefficient of viscosity eta, that is known to us. The inner cylinder has radius A and the outer cylinder has radius B. Now this inner cylinder is spinning with a fixed angular speed of omega 1, and the outer cylinder is spinning with a fixed angular speed of omega 2. Omega 1 and omega 2 are different. So in between, this is a viscous liquid, and assume that the length of this cylinder, the length of the two cylinders is L. We have to find the velocity distribution of the fluid between the two cylinders. It simply means you have to write velocity of a fluid particle which is at a distance r from the axis. So how is velocity of fluid particles changing as you move from this point to this point? How does it depend on r? That is the question. Obviously, because of symmetry, you are supposed to assume that fluid particles do move tangentially only. There is no crisscross movement like this because there is a kind of perfect symmetry out there. So all fluid particles move tangential, tangential to their respective position vector. If a fluid particle is here, it moves tangential, means it moves perpendicular to the radius. So assuming that, you have to write the speed of a fluid particle at a distance r. If you want to give it a try, do give it a try on your own. Here I am proceeding with my solution. I have assumed a thin layer of fluid. Again, I have kept this piece of paper to make your understanding a bit easier. This is the green colored thin cylinder of liquid. It has radius r, and this thickness is dr. Let us think for a moment about the viscous force acting on this layer of fluid. For the sake of ease of talking, let us assume that this cylinder is spinning at lower speed and this one is at higher speed, which means when we move from this point to this point, the speed of fluid layers is increasing. So just for a moment assume that this particular point is having a speed v. Obviously, all the points on this circle will have same speed, it is symmetry. But this particular point will have a slightly different speed. Here the speed of fluid particle is v, and as you move a distance dr outward, the speed changes to, let us say, v plus dv. And this dv by dr, change in speed divided by this distance dr, this is what is known as local velocity gradient. This is velocity gradient. So when you think of this green colored cylinder of fluid which is spinning, the surrounding layer of fluid exerts a tangential viscous force on it. This is a fluid layer. This liquid on this side exerts a tangential force on it. Liquid on this side also exerts a tangential force on it. So right now, think of writing this tangential force due to liquid on one side only. Just think that you are trying to write tangential force acting on this green belt due to liquid on this side. Just think about that. How will you write? Actually, the force is obviously zero. In a sense, force is a vector. Force is a vector, so if you take small patches like this, the tangential force all will add up to 0. But it is not the force in which we are interested right now. We are interested in torque acting on that, basically, not exactly the force. So when this spins, this liquid layer spins, it experiences a torque from the surrounding liquid. Let us write that torque. Please be with me. This is the surface area which is slipping on another layer of liquid. You can think of liquid inside, you can think of liquid outside. As I said, this liquid is exerting force here. This liquid is also exerting a force here. So, this moving, rotating layer of liquid is experiencing an inward torque, a torque due to inside liquid as well as torque due to outside liquid. These torques are slightly different. Is it? In general, they could be different. But are they different here in this case? Not. Why? How do I know that? Because this whole thing is moving with constant angular speed. There is no angular acceleration. If torque due to forces over here and torque due to forces over here are different, which means this green band of liquid will have a net torque which will accelerate it. But one thing is definite, that everything is going with constant angular speed. So there should not be any torque. And this is what we are going to use to get our answer, to write the variation of velocity with r, which means torque should not depend on r. Torque acting on a layer like this should not depend on r. Whatever is the value of torque here, it should be same over here. When r changes by dr, the torque should not change. If torque does not change, the net torque on this green band will be 0, and therefore it will experience no angular acceleration. Please make no mistake. If this angular speed is less and this is high, so as you move from here to here, the speed of fluid layers goes on increasing. So as compared to this point is moving at slightly higher speed, v and v plus dv, as I said, right? Similarly, what I am saying is, in general, we could tend to think that torque experienced by this surface and torque experienced by this surface should be different. But if they are different, then this green belt of fluid will experience an angular acceleration, which is not the case. So torque should be independent of r. This is my logic. This is my argument. So let us write torque at any one layer. Let us say we are thinking of writing torque over here or over here. It hardly makes any difference. Write the torque as a function of r. So this is the surface area, which is 2 pi r into L. 2 pi r into L. It is moving like this, and the velocity gradient here is dv by dr. So surface area into velocity gradient into eta. This is basically, you can say that, sum of magnitude of all the tangential forces. I hope you understand this much. Sum of magnitude of tangential forces. Multiply this with r. R, because we are willing to write torque. Multiply this by r. The tangential forces everywhere act like this. And if you sum the magnitude of these tangential forces, it is equal to this much. That into r is the torque. So this is the torque acting on that green colored cylindrical belt of fluid. Now, what do you want? You want that this torque should not depend on r. How is that possible? That will be possible if this quantity is a constant. Let us say A. Isn't it? This quantity has to be a constant. That means, in a rather simpler language, I should say that dv by dr should be inversely proportional to r square. So if dv by dr is inversely proportional to r square, these two r square will cancel out, and this whole torque will become independent of r, and that is what you want. So the problem has been solved actually. We can figure out this constant by knowing the boundary conditions. You just need to integrate this by separating the variables, and this becomes dv is equal to a dr r square. If you integrate, what is velocity of a fluid particle over here? The same as the velocity of the rotating drum. How much is the velocity here? A into omega 1. So A into omega 1, and similarly on the outer cylinder the velocity will be B into omega 2. Radius changes from A to B. So it becomes B omega 2 minus A omega 1 is equal to A, and this integration will become minus of 1 by R. So I guess this will become 1 by A minus 1 by B. Therefore, you can write capital A as B omega 2 A omega 1 AB by B minus A. So this is the value of capital A. And what are we willing to write basically? We are willing to write speed as a function of R. So again, from here only, I'll again do this integration, but this time starting from this initial point, I will not go up to the outer cylinder. I'll go up to any general distance R, and I will assume that speed is V out there. That means I'll write this integration as A omega 1 to V. When I move from radial distance A to R. Now I know the value of A. So just plug in and you get V as a function of R. So there is A, and obviously this becomes 1 by A minus 1 by R. So in place of A you need to substitute this, you get the value of V. V is A omega 1 plus B omega 2 A omega 1 AB by B minus A into R minus A by AR. I hope you have understood how speed is changing with distance R. In place of speed, one could have asked what is the angular speed, and possibly that will give you a rather simpler expression. But that is it in this question. Hope you enjoyed it. See you in another video.